Hello and welcome to my video. In this video, I'm going to go through the steps and methods of using Inventor HSM CAM software to perform a machining on this turning part here, which is a flange I'm going to use on my spindle on my CNC. Just like in the milling steps, the first steps of the CAD-CAM process is setting up the roughing block, and we do this with the setup option. We select the operation type as turning. We leave it at primary spindle. I have to select the Z-axis, which is on this plane, and I want to flip the X-axis to face upwards. This software also asks us to select the model so that the software knows what's going to be left after the machining. On the stocks tab, I'm going to go with a fixed size cylinder of around 95 millimeters diameters, 45 millimeters length. The model position is going to be offset from the front with a 0 offset so that the work coordinate system sits on the front side of the part. And on the post process, I'm going to leave the program name number at 1001. The comment is going to be a test. And the work coordinate system offset is going to be 0, which corresponds to G54. And by now we have set it up the roughing block. The first operation is going to be a facing. Just like in the milling, we're going to go for the tool, and we're also going to look into the editing of the tools, which is a bit more complex than the milling. So we are going to use standard orientation for turning tools, which is this positioning showed in the picture here. Position 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this one is going to be a roughing tool of orientation 3 in a vertical position. The insert is around 0.8. Everything else is standardized. The holder pretty much the same, standardized. In the setup, we have the orientation on degrees. 0 degrees means vertical, and the compensation type tangent with an M3 direction of the cut, which is forward. In the feeds and speeds, we want to use a constant surface speed, which is around 120, and a feet per revolution specific for turning, which is around 0.1. This is for a given material, that's steel. So we are okay with this tool. We are going to select it. And moving on to the second tab, we don't need a confinement for the facing. The computer automatically detects the face of the part. As for the planes, the computer automatically detects the outer radius, the inner radius, and sets up a standard 10 millimeter clearance. I'm going to switch that one to 5. As in passes, the compensation type, as explained here in computer in control wear and inverse wear, I'm going to go for a wear compensation type and a stock to leave of 0.2 since this is a roughing face-off. And the leads in, I'm going to go for a 90-degree lead in, which is vertical. The tool is going to come down. And the lead out, I'm going to go for a 0 degree, which is 3 o'clock, and the tool is going to exit right. The second operation is going to be a profile. We're going to select the same tool. As for confinement, we're going to select the start and the end of the part, and we're going to leave a -8 millimeter backside offset to make sure we're not going to hit the clamps of the chuck that's going to hold on to the roughing part. The planes again are okay. We're going to go for a 5 millimeter clearance. The outer radius is set as the stock outside diameter, and the inter radius we're going to change to selection, and we're going to select this chamfer here. As for passes, again we're going to go for roughing passes of around 1.5 millimeter step down. and the stock to leave is going to be at 0.2 millimeters, and the leads in are going to be a 3 o'clock positioning, so the cutter enters from right to left. That means 0 degrees here. And for the lead out, we're going to go with 90 degrees so that the cutter exits 12 o'clock, which is upwards direction. And here we have our profile. Now, because we're going to move into the inside of the part, we can change the view from full to half section view. We're switching into the model and we are selecting the plane, which is this plane. Click OK, and now we can look inside the part. The next operation is going to be a drilling. We are going to go with the 23 diameter drill. We can select the whole faces, and we can also merge the segments. The bottom height is going to be the whole bottom, but I'm going to include the tip of the drill manually. It should be around -8 to be sure. And the operation type is going to be drilling rapid out. And here we have our drill to the center of this flange. The next operation is going to be roughing out the inside of the part. We do that with the profile operation. Again, we're going to select the tool as this boring bar, which is positioning 2 in the horizontal orientation. The mode is going to be inside profiling this time. We're not going to allow grooving because it's going to try to go into this grooving cut here. The confinement is going to be from the front side to the back of this radius here, and I'm going to introduce a 1 millimeter back side stock offset. The planes are going to be selected. The outer radius is going to be this chamfer, and I'm going to give it a 1 millimeter offset to make sure it's going to do the whole chamfer. The inner radius is going to be this back radius here, and the clearance I'm going to select that inner limit -1 millimeter. As passes, I'm going to deselect finishing. We're still doing the roughing. The step down is going to be 1.5 millimeters, and the stock to leave is going to be 0.2. As for lead in and out, the lead in entry is going to be at 0 degrees, and the lead out it's going to be at 90 degrees with a linear lead out of 0.5. And here we have our profiling operation. Now, if we want to do finishing on these profiles, we can go into the roughing profiles and create a derived operation, which is going to keep all of the settings, and we can just change it from roughing to finishing. And here we have our outside profile for finishing. The inside profile for finishing. And the front profile for finishing. Now for the grooving, we select the groove option. The tool is going to be this one. Everything is set on the tool. The confinement are going to be these two radiuses. The planes are going to be selected again. The outer radius is going to be this diameter. The inner radius is going to be this diameter. And the clearance is going to be the outer limit plus 0.5. Now for the passes, I'm going to go for a finishing pass with a 0.1 step over, a roughing clearing pass, no packing, and only down direction. And for the leads, I'm going to go with a 0.5 lead in of 30 degrees angle so it gets a smooth touch on this radius. And the lead out is going to be again a 0.5 with a 90-degree. And here we have our grooving passes, and we're going to do the same for the inside groove. And using the derived operation, all I had to do was change the orientation of the tool, and here we have the inside grooving. By now we are ready to simulate, and we are going to click setup and simulate. We're going to put the stock on show transparent and the toolpath for the operation, and we can simulate the toolpath that we have set it up by now. Now the next operation is going to be the inside thread. We're going to do this with the thread operation. We're going to select the tool, this one. We want the mode to be inside threading. We have a use of a feet per revolution which is specific to threading. This is going to be the thread face, and as confinement I'm going to leave a front side stock offset of 7.5 millimeters. That's the position from which the cutter is going to start the threading operation. And I'm also going to put a backside stock offset of 10 millimeters, but applied from the front because I know the thread is 10 millimeters deep. As for the planes, I'm going to select the inner radius as this face. The outer radius is going to be the inner limit plus 1.5 millimeters, and the clearance is going to be the inner limit minus 1 millimeter. As for the passes, the thread depth is 0.182, specific for 1.5 millimeters thread pitch. We are going to use a cycle, and the number of step downs is going to be around 10. As for leads in and out, we want a full retraction, and let's look at our thread profile. This is the thread profile. Now for the outside thread, I'm going to switch the view to normal. As we can see, this outside thread is left-handed from the thread spirals, and we are going to use a left-handed thread operation. And this is the tool. We are going to edit it. So this is the general information. This is the insert where we select the pitch. This is the holder, and all we have to do is select left-handed. In the setup, we see we want a reverse spindle, which is an M4 code, and the orientation we want at 0 degrees, which means the tool is going to sit vertical. And in feeds and speeds, we want a feed per revolution specific to threading. Now, this tool is set. We are going to select it. The mode is going to be outside threading. We're going to use feeds per revolution. The thread faces are this one, and the front side stock offset is 7.5 millimeters, which is where the cutter is going to start the cutting. The back side stock offset is 10 millimeters, but applied from the front because the thread is 10 millimeters deep. The planes are selected, the outer radius as being this face. The clearance is this face plus 1 millimeter, and the inner radius is again the outer limit minus 1.5 millimeters. In the passes, we select the left-handed thread this time with a thread depth of 0.182 millimeters. We have an already selected 1.5 millimeter thread pitch. We want to use a cycle, and the number of step downs is 10. And this is our tool path. Now we can simulate the tools separately. We're not going to show the stock. We can see it's showing some collisions here because the actual insert is touching the model, but we know that is not the case. And this is the inside right-handed thread. And this is the outside left-handed thread. Notice how the insert sits on the left side of the holder. And these are our inside and outside threads completed. Now, after we have set it up all the tool path, we can look into the tool library and order the tools. I've noticed that the finishing profiles were done with the roughing tool, so I've added finishing tools. Again, just like I showed in the milling video, we can go into the tool directly and change the feeds and speeds. For example, this is a roughing tool of 120 meters per minute, cutting surface speed and a 0.1 feet per revolution. Just the same, we can look into the finishing and we see a surface speed of 180 meters with a 0.05 millimeters per revolution feed per cut. This is for a given steel material. And in the threading, I've went with a normal 500 rotations per minute and the 1.5 feet per revolution that equivals the pitch of the thread. And after we've changed the feeds and speeds and ordered out the operations, we have a roughing for the facing, an outside profile, a drill, an inside profile. Now the finish for the face, the outside profile, and the inside profile. The groove have roughing and finishing included in the operation, and the threads, the inside and the outside threads. Now we can click setup and simulate and see that in the information we have this part completed in 1 minute. We are ready to produce the setup sheet. The setup sheet is going to include all the tools that go into the machining and the order in which they perform the machining. This is good for the operator to take a quick look at a resume of the whole program. And I want to mention that this part also has these holes here that I've tried to post-process, but the post-processor on this software doesn't support a Z-axis. So we are going to post-process only a 2-axis turning. We click on the post-process, we select turning. Our options are this Fanuc turning generic, which I said is only good for 2-axis turning, and we can post-process. Now we can backplot all the operations in Inventor HSM. We can re-edit manually into the code directly, and we can see the result of that editing. The first thing I've noticed as a CNC programmer is that the speeds are way off. For instance, this G50 S6000 means that there's a spindle limit of 6,000 revolutions. But I know I went into the options of the program and selected a maximum spindle speed of 3000, but I guess the post processor doesn't translate that. Also, the surface speed of 120 is at meters per minute, and the post processor translated into millimeters per minute. So this G96 is a constant surface speed, and it should be 120, not 120,000. So we can edit this manually and change the limit to 3000 revolutions and the constant surface speed to 120. The third thing I noticed is that it's not using cycles. So this is a positioning point by point in the X and Z plane of the tool. For the facing, just to see the operation, we can put in a M30. It signals that the program ends here, and it's only backplotting the first operation. These positions can be simply changed to a cycle instead of being positioned point by point like the post processor is doing. And this is an example of a facing cycle, the G72 cycle, that says this W means the depth of the cut, this R1 is the lead out distance after each cut, this P31 to Q33 corresponds to this N31 and N33 that have to include the toolpath for the facing operation, and this U and W are the allowances for the X and the Z, and FO1 is the actual feed of the cut, which is 0.1 per revolution. Now, if I delete the point by point cycle, this is our cycle in which we can change the depth of each cut. We can change the distance from which the tool is going to start cutting depending on the allowance we have on the rough block, and it's much simpler to use. And this is an example of the outside profiling that again the post processor has translated in point by point positioning of the tool to make all the roughing passes. If we want to change something, this is going to be very hard to impossible in this code. So there is a roughing cycle for that one as well. I have cleared out the point by point positioning so we can look at the roughing cycle. This is the tool getting called out with the machine and tool settings, the first positioning here X104 Z5, and then the roughing cycle, the G71. Just like the facing cycle, this cycle is for roughing a profile, and it specifies the U depth of the cut, the R lead out distance after each cut, the P, Q correspond to the N, that's the start of the tool path, to the N, that's the end of the tool path. The tool path has to start at the lowest X and end at the highest X, and mention all the X's and the Z in the order of the tool path. Now we have the U and W for the allowance on the X and the Z, and the F, which corresponds to the feet per revolution. In this way, we have set the profile, and we can change the depth of the cut, the feed, the starting point on the Z direction, the starting point on the X direction, and depending on the roughing block, this cycle it's much simpler to use. And this is an example of a thread cycle. The cutter enters right and cuts towards the left. I can see that the post processor is using a G92 cycle. This means that the cutter is always going to enter down. If we look at a thread profile, the cutter entering straight down means that it's going to cut on both sides, and this is going to leave a rougher finish because it's most likely to vibrate. That's why it's good that the cutter enters one side and follows the profile angle of the thread. This is what the G76 cycle is for. To explain the cycle, this P02 means the number of finishing, the 0060 means the geometry of the thread, in which we have the 60 degrees angle here that we can change to 50 or other angles. We have the depth of the finishing. The start of the thread is X56 and it ends at X54 on the x-axis and Z5 to Z-11 on the z-axis. This P812 is the height of the thread, and this F1.5 is the feet per revolution, which corresponds to the thread pitch. And in this way, if we take out the G92 cycle, we can see that the cutter is going to follow the angle of the thread and perform the roughing and the finishing. Now, if we want to tackle the problem of these 6 holes here, we're going to need a driving tool and a C-axis on a 3-axis turning. In the software, we can do this with the drilling operation. We select the tool, the 9mm drill. We select a hole face and a top height. On this face, we're going to leave the whole bottom with an offset for the tip included, and we're going to use the drilling rapid out option. Notice that anywhere on these options we don't have a wrap option, so we are going to use the pattern, a circular pattern. We're going to select the axis, tell it we want 6 holes that are equally spaced, and again we do not have a wrap option. But the software is going to show us our 6 holes, and we want to post-process this and see a C-axis in the post-processing code. And we can see in the back plot and in the code that we do not have a C-axis included. So we can change this inconvenience by adding a C-axis ourselves. We're going to end the program here at M30. We are going to introduce a G28C0 for the first positioning of the C-axis. We're going to put the C0 in the cycle, an optional M89, which is going to block the spindle while the hole is being performed. And after this, we're going to put the other degrees, C60, the C120, and so on. And here in the back plot, we can see our 6 holes performed by manually editing the cycle to introduce a C-axis. This is understandable for me. I know this isn't a professional post-processing unit. I'm borrowing the software over the internet from a school's computer. But in this way, I've managed to go through the steps and methods of using a CAM software to produce and explain the CNC code used for manufacturing a component like this on a CNC equipment. In this case, a turning. In my next video, I hope to come across a post-processor editing software so I can edit the post-processor to make it spill out the CNC code like I want to. But in the meantime, I hope you enjoyed my video and remember to have fun at work.